Hello everyone, so this is the second lecture on the chapter atomic structure. Okay, so in the last lecture we discussed till frequency and time period calculation by using Bohr's postulates or by using Bohr's theory. Now we will see energy level of hydrogen atom. Energy level of hydrogen atom. Okay, so the energy relation that we derived by using Bohr's postulate or Bohr's theory is minus 13.6 divided by n square electron volt. This was for hydrogen atom. Okay, now for n equal to 1, you see E1 becomes minus 13.6 divided by 1 square is minus 13.6 electron volt. So you call this energy of electron in ground state. Okay, this is energy of electron in ground state of hydrogen atom. Next, for n equal to 2, you have E2 equals to minus 13.6 divided by 2 square, which will give you minus 3.4 electron volt. This is energy of electron in first excited state. Okay, so energy of electron in first excited state. Okay, you need to remember, like when we say first excited, it means n equal to 2. Okay, first excited state is n equal to 2. Then we have n equal to 3. E3 equals to minus 13.6 divided by 3 square. If you divide 13.6 divided by 9, or if you divide 13.6 by 9, you get minus 1.51 electron volt. Okay, so this is energy of electron in second excited state of hydrogen atom. Then you have n equal to 4. E4 equals to minus 13.6 divided by 4 square, that is 16. This will get you minus 0.85 electron volt. This is energy of electron in third excited state. Okay, energy of electron in third excited state. Alright, so you can try out for 5, 6, etc. Now for n equal to infinity, E infinity is minus 13.6 divided by infinity square. This will get you 0. Okay, this is energy of electron at infinity. Energy of electron at infinity. Alright, I hope these energy values are clear and you have to remember them. Now we'll just put them in a diagram. Okay, I'm just copying this diagram. So you see here, these are the various energy levels. Okay, this is n equal to 1, this is 2, 3, 4, 5, various n numbers, and the energy values. Energy of electron in n equal to 1 is minus 13.6, then you have minus 3.4, minus 1.51, minus 0.85. For n equal to 5, it comes out to be minus 0.54, and so on. For n equal to infinity, you'll have energy value as 0. Okay, I hope this energy value calculations are clear. You can try working the energy level calculations for helium plus and lithium 2 plus by using the relation minus 13.6 z square by n square electron volt. Okay, you can find out the various energy levels for helium plus and lithium 2 plus. For helium, when you use helium plus, then in place of z you'll have to use 2 square, and in case of lithium 2 plus you'll have to use 3 square. Here z value will be 3. Okay, so those are the hints for working them. Next we can see line spectra of hydrogen atom. Line spectra of hydrogen atom. So Bohr's third postulate, what does it say? Bohr's third postulate, whenever an electron jumps from a higher orbit to a lower orbit. Okay, electron jumps from, say, higher orbit to a lower orbit. then it will emit photons, okay, whose energy is h nu, and this, the initial energy state, you call it as EI, and the final energy state where it jumped into, you call it as EF. So in accordance with Bohr's third postulate, you can write down h nu equals to EI minus EF, okay. Now this can be written as hc by lambda equal to, now what is the value of E? Value of E is minus 2 pi square m k square e to the power 4 divided by n square h square. Now this was E initial, right? Therefore we write down Ni minus this minus comes from the relation, and this negative is already there, like this negative is already there in the energy relation, energy expression, energy in nth Bohr orbit. So minus 2 pi square m k square e to the power 4 divided by, now we write down nf square h square. Now the second quantity is positive, right? So you can write down 2 pi square m k square e to the power 4 divided by n will be there inside the bracket, divided by h square, and you have 1 by nf square minus 1 by ni square. Now from the left side you can bring this hc, okay, to get h cube c, and here you have 1 by nf square minus 1 by ni square. Now this entire quantity is a constant. You see, pi is a constant, mass of electron m, k Coulomb's constant, E charge of electron, h is Planck's constant, and c is speed of light. Once you put the values and do the calculation, you'll get a value which you call as Rydberg constant of hydrogen atom, okay. So we are writing here RH 1 by nf square minus 1 by ni square. This is 1 by lambda. So this is the formula for hydrogen atom. For hydrogen like system, this relation will become RH Z square, okay. For helium plus and lithium 2 plus, this will apply, where Z is the atomic number of the hydrogen like system. So 1 by nf square minus 1 by ni square. So again, this is one more relation you have to remember. Now this RH thing, it was 2 pi square m k square e to the power 4 divided by h cube c, right? So once you put the values and do the calculation, you will get 1.097 into 10 to the power 7 meter inverse, okay. So you call this as Rydberg constant of hydrogen atom. So this equation, the first equation, you call this equation as Rydberg formula, okay, for hydrogen atom spectrum. Now you also call 1 by lambda as wave number. You denote that with nu bar, okay. So that is also called as wave number. So the same relation can be written as nu bar equals to RH 1 by nf square minus 1 by ni square. So based on this, we have various spectral line series of hydrogen atom. So various spectral line series of hydrogen atom. Now I'll just copy down this diagram, okay, a very small representation which will help you to remember the various informations that you need here. So you see, here we have written like L, BP, 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 BP repeats, clear? So L is Lyman series, B is Balmer series, P is Paschen series, B is bracket, and P is P fund. So these are the n final numbers. That means electron will transit, electron will jump from any higher states to these respective n final numbers for the respective series, okay. And n initial, like when n final is 1, then n initial will be any number between 2 and infinity, or infinity and 2, okay. So here when n final is 2, then n initial will be any number between infinity and 3. So I'll be showing you one calculation or like two calculation, and the others will be homework, okay, that you can work it out yourself. So here like you'll get the maximum wavelength as 1216 angstrom and the minimum wavelength as 911 angstrom, Okay, so maximum wavelength you'll get when the energy is minimum, like when the transition is from 2 to 1, you'll get a photon released, a minimum energy photon will be released. In that case, the wavelength of the photon will be maximum, that is 1216. Similarly, in Balmer series, 3646 angstrom will be the minimum wavelength and 6563 angstrom will be the maximum wavelength. Okay, so we'll see them, and well, these wavelengths, they lie in ultraviolet region. So Lyman series lie in ultraviolet region, Balmer series lie in visible region. Okay, so out of the visible region, again you have to remember one more information, that 4 photon emit, or you can say 4 photons are released which lie in visible region, and the remaining 3 are infrared region. Okay, so let's see Lyman series. Number 1, Lyman series. So in Lyman series, transition will happen to n final 1, and n initial can be like 2, 3, 4 dot dot up to infinity, right? So when the transition is happening from 2 to 1, you see this is the closest. Okay, 2 to 1 is the closest out of all energy levels. So energy of the emitted photon will be h nu minimum. In that case, wavelength will be maximum. Okay, so if you want to calculate this maximum wavelength, then we'll apply RH 1 by n f square. F is 1 by 1, right? 1 square minus 1 by 2 square. Okay, so what is it giving you? It is giving you 3 by 4, 3 RH divided by 4. Now if you do lambda max equal to 4 divided by 3 into the value for RH is 1.097 into 10 to the power 7. Yes, so this calculation will get you 4 by 3 is already 1.33, right? So 4 divided by 3 divided by 1.097 will get you 1.215 into 10 to the power minus 7 meter, and this is 1215 angstrom you can write down. Now this is actually 1.2154. okay, so this angstrom you can write down. We previously I might have written 1216. okay, so for convenience of calculation we at times use it as 1216. okay, however it doesn't matter, you write down 1215 or 16, it will matter at a very negligible scale. So the maximum wavelength value is this. Now when the transition happens from, now this was for 2 to 1, right, infinity to 1, you see infinity to 1, the energy or the photon which will be released will have maximum energy. In that case, E will be equal to h nu maximum. Now h nu maximum is hc by lambda minimum. okay, so 1 by lambda minimum will be equal to RH 1 by 1 square minus 1 by infinity square. So what you are doing is like RH only, you have here, you have RH here, and lambda minimum is equal to 1 by RH, which is 1 by 1.097 into 10 to the power 7. So 1 divided by 1.097 will get you 0.9115 into 10 to the power minus 7 meter. okay, so that will get you 911.5 angstrom. okay, so this is the minimum wavelength photon, or wavelength of the photon, minimum wavelength of the photon when the transition happens from infinity to 1. okay, so similarly you can calculate for Balmer series number 2, Balmer series. So Balmer series n final number is 2 and initial number is 3, 4 dot dot up to infinity, right? So when the transition happens from like 3 to 2, this is the closest in case of Balmer series. okay, then your energy emitted will be minimum, yes, and wavelength will be maximum. Wavelength of the photon emitted will be maximum. So in that case also, if you want to calculate like RH 1 by nf square, 1 by 2 square minus 1 by 3 square. okay, so that is giving you 9 minus 4, yes, 9 minus 4, 5 by 36. 5 by 36. Now if you take the reciprocal, equals to 36 by 5 into 1.097 into 10 to the power 7. Okay, so 36. This calculation will get you 6.563 into 10 to the power 7, sorry, minus 7 meter. So this is 6563 angstrom we can write down into 10 to the power minus 10 meter, right? So this is lambda maximum. Now for minimum, like infinity to 1 transition, photon emitted will have maximum energy. Yes, and that is hc by lambda minimum. So hc by lambda minimum, 1 by lambda minimum is equal to RH 1 by 2 square minus 1 by infinity square. Okay, so that is equal to RH divided by 4. So lambda minimum is equal to 4 divided by 1.097 into 10 to the power 7. So 4 divided by 1.097 will get you 3.646 into 10 to the power minus 7 meter. So that is 3646 into 10 to the power minus 10 meter, that is angstrom. So lambda minimum value is this. Okay, so you will try calculating the other three also, like Paschen, bracket and P-fund. Just the calculation method you need to know. Okay, and of course the first one and the second one, Lyman and Balmer, you have to remember, you have to memorize the value for minimum and maximum wavelength. Okay, so I am not going into the other three, I am leaving that for you to work upon. Next I will show you the diagram. So two diagrams are there. Okay, so the second diagram is like easy to relate, but the first diagram is easy to draw. Okay, this is easy to relate because we usually assume that atom has nucleus at the center and it has these energy levels or the orbits around it. Okay, so it looks like this. Now whenever the transition, electron is jumping from 2 to 1, okay, or 3 to 1 or 4 to 1, 5 to 1, 6 to 1, all the photons that will be released due to this transition, okay, they will lie in Lyman series. Okay, next Balmer series, like 3 to 2, 4 to 2, 5 to 2 and so on, they will lie in Balmer series. Similarly you will have Paschen, Paschen, bracket and P-fund. Now this is like, this portion is shown, this is for excitation. We'll see what is excitation. Okay, so external energy will be received by the electron in the ground state, and then depending on what value of energy is received or what energetic photon is received, the electron will jump to n equal to 2 or 3 or 4 or 5 and so on. Okay, now if sufficient energy, if tremendous amount of energy is received, and due to that, okay, precisely this excitation, by definition this has to happen from the ground state. Okay, now this is like absorption, emission is shown, absorption and emission spectra is shown. This is a different thing, we'll discuss towards the end of the chapter. Now when we talk about excitation, this has to happen from the ground state. Now if an electron lying on ground state, if that receives some external photon, and if it becomes free totally, it goes to infinity, you call that condition to be ionization. Okay, ionizing. So that energy which will be received and for which the electron becomes free absolutely, you call that energy as ionization energy. All right, so the same, this like de-excitation thing, it can be shown in terms of this diagram also. This diagram is easier to draw. This is n equal to 1 ground state, n equal to 2, 3, 4, 5, 6, and this is like infinity. Okay, this space is infinity. So these are all excited state, except n equal to 1 is ground state and the others are called excited state. So whenever electron jump from any higher state to ground state, you call that as Lyman, Balmer, and for n equal to 2 you call that as Balmer, Paschen, bracket and so on. Okay, I hope this is clear. I am not going into elaboration for this, and the energy values are also written over here, you can see. Okay, so after this we have de Broglie's explanation of Bohr's second postulate. Okay, so de Broglie's explanation of Bohr's second postulate. Now you see Niels or Louis Victor de Broglie, he said that in his explanation he said that electron or any particle, when it behaves like a wave, you can assume the particle as a wave of this pattern. Okay, as a string you can assume, like you have a string which is fixed on one end and you give a jerk to this string. Okay, this is string and you give a jerk to this string, then you get this kind of wave pattern. Yes, the very next moment the wave pattern will become like this. Okay, and in this way it will keep on fluctuating. So the point where you had the crest, the very next moment you have the trough there. So similarly here also you can see the electron is, now you don't have a particle here, you have this string, a closed loop you can imagine. Okay, and when it is fluctuating, then once the crest will be here, the very next moment the trough will be here. Okay, so de Broglie told that electron is not behaving as a particle here, but it is entirely behaving as a wave. Now if you have say n number of wave here, like from here this point to this point, this point to this point, this is one wavelength, isn't it? Now again this point to this point you have another wave. All right, so n number of complete wave will have n lambda as the wavelength, and that is covering like 2 pi r circumference. Okay, so that is equal to 2 pi r. Now by de Broglie's wave relation, n lambda can be written as h by mv, that is equal to 2 pi r. So you can do some changes, like you can send mv to the right side and bring 2 pi on the left side, so you get nh by 2 pi equal to mvr. Now what is this mvr? Mvr is the angular momentum value. So this is the expression that we need, and therefore Niels Bohr, he said that electron can exist only in those orbits whose angular momentum satisfies this relation. Okay, where n is any number from 1, 2, 3, 4 and so on. So angular momentum of the electron is quantized. It has certain fixed values decided by h by twice pi, twice h by twice pi, thrice h by twice pi, 4h by twice pi and so on. Okay, so that is your de Broglie's explanation. Now we go to excitation energy. Excitation energy. So when you call as excitation, what do you call as excitation? Electron jumps from ground state to any higher state when energy is received from the outside. Now in that case you'll call this as initial because the electron was resting in the ground state previously, and the energy level where the electron jumps into, you call that as energy final energy, and the energy which is absorbed you call that as E. Okay, that is called the excitation energy. So the relation will be EF minus EI. Remember, in Bohr's third postulate, de-excitation was happening. Electron was jumping from this part to this part. There we called this outer energy level as EI, inner energy level as EF. Again, there also we have done EI minus EF. So only the name is changing, but we are always subtracting the inner energy level value, inner energy level from the outer energy level. It applies for excitation as well as de-excitation. So that's a simple way to remember this. Now first excitation, what do you call as first excitation? You will write that as E first. Okay, E1 is ground state energy, E2 is first excited state energy, but E second is second excitation energy. That's the difference between the two. When you say first excited state energy or ground state energy, you are talking about the energy of a certain level. But when you are talking about excitation energy, you are talking of the transition energy that is required, the energy that is required for transition of electron from one state to another. So E first is, you call that as E first when the electron goes from 1 to 2. So it will be E2 minus E1. Now E2, the value you remember, I hope. E2 value is minus 3.4. E1 value is minus 13.6. Yes. So this calculation gets you 10.2 electron volt. So 10.2 electron volt. If you supply 10.2 electron volt to an electron in the ground state of hydrogen atom, okay, then it will jump to first excited state. Electron will jump to first excited state. Now you have second excited state. What do you call as second excited state? When the electron jumps from 1 to 3. In that case, E second, we write down E second, that is E3 minus E1. E3 minus E1. So E3 value is minus 1.51 minus E1 value is minus 13.6. This gives you 12.09 electron volt. Okay. So when you supply 12.09 electron volt energy to an electron in the ground state of hydrogen atom, the electron will jump to n equal to 3. Alright. So similarly, you can calculate a third excitation, fourth excitation, and so on. Okay. Now we have this excitation potential. Excitation potential. Now this is just the potential. This is like measuring the same thing, the potential difference. Okay, the potential difference required to excite an electron to go from ground state to any higher state. Alright, to any higher state. The potential difference required. So first excitation potential, that is like 10.2 volt. Okay, 10.2 electron volt was the first excitation energy. So when calculating potential, you write down 10.2 volt. Second excitation potential is 12.09 volt, and so on. You can calculate the third and the fourth one. Okay, so after this we have ionization energy. Ionization energy. So ionization energy, in ionization energy, what do you do? Electron becomes free from ground state, electron will go to infinity straight away. Now for that, whatever energy is required, you call that as ionization energy. Therefore, ionization energy, now what is the energy of electron at infinity? So we'll be doing outer energy value minus inner energy value, right? So E infinity minus E1 is your relation. So for hydrogen atom, or for any atom in fact, the electron will have zero energy at infinity. So for hydrogen atom, we are calculating ionization energy. IE equals to 0 minus 13.6. So 13.6 electron volt is the ionization energy for hydrogen atom. So what it means is that you have an electron in the ground state of hydrogen atom. Now you supply 13.6 electron volt energy at least. Okay, you can supply greater than that. So you supply at least 13.6 electron volt energy, then the electron becomes free. It becomes very energetic to jump out of the atom, okay, and become free. So this is what you call as ionization energy. Now, like one difference that you have between ionization energy and excitation energy is that a single atom can have many excitation energy values, but only one ionization energy value. Okay, so this needs to be remembered. Next is ionization potential. Okay, ionization potential you write down as IP. Okay, so here it is same, the definition is pretty similar to excitation potential. The potential difference required to knock out an electron from the ground state of the atom. So for hydrogen atom, the ionization potential will be 13.6 volt. Okay, so you can find out for helium plus and lithium 2 plus. Okay, so after this we have the last topic in the chapter, which we call as atomic spectra. So before explaining the things, we'll just recall a couple of things. You see, if an electron jumps from 2 to 1, okay, what happens? 10.2 eV energy is released, okay, because this is minus 13.6, this is minus 3.4. Now if an electron jumps from 1 to 2, then it will need 10.2 electron volt of energy. Okay, so the thing is that whatever amount of energy is released when an electron jumps from a certain level, say 2 to 1, then the same energy will be required to jump from that ground state to the same level. Okay, so similarly it goes with for 1 to 3. For 3 to 1, if an electron jumps from 3 to 1, then the energy released will be 12.09 electron volt. Okay, because this value is minus 1.51 eV and this is minus 13.6 eV. Now if an electron has to go from 1 to 3, then it will need 12.09 eV. Okay, so based on this we'll understand this line emission spectra and line absorption spectra. So you see, this is continuous spectrum. Like when you have a prism and you allow white light to pass through the prism, you get continuous spectrum. What is absorption spectrum? Now absorption spectrum happens when electron excites. Okay, electron excites from ground state to any higher state, then absorption spectrum happens. Emission spectrum happens when electron de-excites. That you have to remember. This happens during de-excitation. Okay, the Bohr's third postulate applies here, and this happens during excitation. So a diagram is shown over here that you have a hot body, a light source. Now light is coming out through that source, you pass it through prism directly, you get the continuous spectrum. Now you pass it through a cloud of cooler gas, say this gas is hydrogen, and cold gas, that means the hydrogen gas is in ground state. Now when the high energy radiation passes through this, then what will happen? The hydrogen gas will be excited because it has received energy. So when it excites, and then when this white light passes through this prism, then what happens? The white light is dispersed into the constituent colors, but you find some dark lines there. The question is, what happened to those dark lines? I mean, what happened to those colors over here? That means you have some light present over here. It means that photons are there, photons of certain frequency or certain wavelength are present here, and in the dark lines no photons are present. That means the photons are missing here. Where did the photons go? The photons are utilized to excite this hydrogen gas. Since the photon got utilized over here, the photon did not exist here. Okay, they go missing. All right, this is like when you come to school, when you are supposed to come to school, and if you go somewhere else in the class, your space will be empty, right? You will go missing, then your space will be empty. So here also the photons are missing, they are utilized somewhere else. So that is one condition. You call this as absorption line spectrum. So in absorption spectrum, you have dark lines on a bright background. Okay, now one more thing I would like to add here is that these particular dark lines, like this red light, isn't it, red light has low energy and high wavelength, or low frequency and high wavelength. So low energy is required for closer transition, isn't it? Say if we take an example like hydrogen, in hydrogen gas, an electron is jumping from 1 to 2. Less energy will be required in comparison to 1 to 3. Yes or no? So say this dark line, this photon which went missing here, this is utilized for exciting one atom of hydrogen here, where the electron went from 1 to 2. Now understand one thing, that if the same electron de-excites, it will release exactly the same wavelength photon. Okay, the photon which was missing, it will release that. So we'll see that in the other situation here, emission spectrum. Now again, white light is passing through this hot gas, this cold gas here, and this gas is excited. So after the gas got excited, what happened? The gas is allowed to de-excite. Okay, so when the gas went or underwent de-excitation, what happened? Then certain specific colors were emitted, and that was obtained on a dark screen. Now why certain specific colors? Because you see, when you say hydrogen gas is excited, it basically means that you have electrons in n equal to 2, you have electrons in n equal to 3, you have electrons in n equal to 4, and so on. So if an electron from n equal to 2, it jumps to ground state, then we will receive a photon whose energy will be 2 eV. And exactly this photon, this particular energy photon, was absorbed when the electron jumped from 1 to 2 in this situation, in case A, and therefore this photon went missing here. And here the same de-excitation, when it happened, this photon became existing here. Okay, therefore you see these dark lines and bright lines, they are exactly lying on the same wavelength. They are exactly lying on the same wavelength. That means what? If a certain photon, say for this particular line, if the photon is absorbed, or if the photon is used to excite the electron from 1 to 3, then for this particular bright line, the photon, when the electron was de-excited from 3 to 1, this photon which was absorbed over here, this is released here. Okay, this got released, and therefore you can see a bright line here. Okay, so in case of emission spectrum, you actually see bright lines on a dark background, and in case of absorption spectrum, you see dark lines on a bright background. So this you need to remember. So again, if I repeat this part, like why you have a dark line and bright line here, why they correspond to the same wavelength, it is like when the white light passed through this gas, some photons were stuck here, they were utilized to excite the hydrogen atom. Now if one photon is used, if a 10.2 electron volt photon is used to excite electron from n equal to 1 to 2, then you don't see this photon here, because it has been used here. Okay, now in this case, the hydrogen gas was excited, and then in the second stage you allow the gas to cool down. When the gas cooled down, if an electron jumped from 2 to 1, then a 10.2 electron volt photon appeared. Okay, so therefore you see this bright line. If an electron jumped from 3 to 1, then a 12.09 electron volt photon appeared. Okay, and therefore you see another bright line here. So again, these lines will also correspond to certain transitions. Alright, so if you understand two things, like two excitations, 1 to 2, 1 to 3, and 2 to 1 and 3 to 1, then I hope this will be pretty clear. Okay, so this was the atomic spectra thing, the emission spectra actually, okay, which could not be explained. Was it emission spectra? Yeah, it was emission spectra during excitation. this was the thing which could not be explained by Thomson's model also, which could not be explained by Rutherford's model also. This was a failure for both of them, and finally Niels Bohr could explain this phenomena, okay, called atomic spectra. So thank you. In case there are any confusions, we'll discuss that in live class, and I guess you are ready for the questions now. You'll try the questions and then we'll discuss that in the class again. Like I'll upload another talk on that.